Hello everyone, and welcome. I'm excited to kick off our presentation today on atoms and molecules. On this first slide, you'll see the title of our session, Atoms and Molecules, along with a subtitle that highlights the fascinating world of the building blocks of matter. Over the next few slides, we'll explore what atoms and molecules are, how they interact, and why they are so important in chemistry and beyond. So, let's get started and dive into the basics of the universe at its smallest scale. Thank you for being here today. On this slide, you'll see the contents of our presentation, which covers the fascinating world of atoms and elements. We will start by exploring the first 20 elements and their symbols as introduced by Dalton. Then, we'll delve into important laws like the law of conservation of mass and the law of constant proportion, which help us understand how elements combine to form compounds. We'll look at how to write chemical formulas and understand the molecules of elements and compounds. Atomic mass and the question of how big atoms really are will also be key points. We'll discuss Dalton's atomic theory and how atoms exist in different forms and states. The concept of valency and how atoms bond will be explained clearly. Throughout, we'll connect these ideas to the modern symbols of elements and the history of atomic theory, showing how scientific understanding has evolved. Our goal is to give you a comprehensive overview of these fundamental concepts that form the foundation of chemistry. So, let's get started and explore each of these exciting topics together. Good morning, everyone. Today I am pleased to introduce a student from our class ICSE, Raksit Gupta. Raksit is here to present his work, and I am sure you'll find his insights engaging and informative. This slide highlights the student's name and class, setting the stage for the presentation. Remember, each student's contribution is a valuable part of our learning journey, so let's give Raksit our full attention as he shares his knowledge. Let's explore the fascinating history of the atom. There are two fundamental laws of chemical combinations that were established after extensive experimentation by Antoine L. Lavoisier and Joseph L. Proust. These laws laid the groundwork for our understanding of how elements combine to form compounds. Around the same time, ancient Greek philosophers like Democritus and Leucippus proposed similar ideas. They introduced the concept of the atom, which means indivisible or fundamental particles. They called these particles parmanu, meaning tiny, indivisible units. Another philosopher, Pakadhakatayana, expanded on this idea by suggesting that these particles exist not just as isolated units, but can also be found in combined forms. This early thinking about atoms and their arrangements was quite advanced for its time. Interestingly, both Indian and Greek philosophers were curious about the unseen, unknown forms of matter. For example, around 500 BC, an Indian philosopher named Maharishi Kanad hypothesized that if we keep dividing matter, what he called padarth, we would eventually reach the smallest possible particles. He believed that beyond this point, further division would be impossible. This concept of the smallest particles, or the ultimate indivisible units of matter, is what we now recognize as the foundation of atomic theory. It's fascinating to see how these early ideas laid the groundwork for modern chemistry and atomic science. Now let's take a closer look at the two fundamental laws that help us understand how matter behaves. First, we have the law of constant proportion. This law tells us that in any chemical compound, the elements are always combined in the same fixed ratio by mass. For example, water is always made up of 2 parts hydrogen to 1 part oxygen, regardless of where it comes from. Next, we have the law of conservation of masses. This is a core principle that states mass cannot be created or destroyed in a chemical reaction. So, the total mass of the reactants equals the total mass of the products. Both of these laws are crucial because they form the foundation for understanding chemical reactions and how substances interact. They emphasize the consistency and predictability in chemistry, which is essential as we explore more complex concepts. These laws connect directly to the overall theme of scientific laws that govern matter and help us predict and explain chemical behavior reliably. Now let's measure again. Notice that the mass of the flask doesn't change after the chemical reaction. This is an important observation because it hints at a fundamental principle in chemistry, the law of conservation of mass. The key takeaway here is that mass is neither created nor destroyed during a chemical reaction. So, whether we start with our reactants or end with our products, the total mass remains the same. Next, I want you to measure the weight carefully. After that, tilt and swirl the flask gently to ensure the reactants mix thoroughly. Now, let's prepare our materials. Take 1.43 grams of sodium carbonate and place it into a conical flask, marking this setup as B. Make sure to follow the diagram shown here to set everything up correctly. Then, take 1.25 grams of copper sulfate and put it into an ignition tube, marking this as A. We can verify this principle through an activity. By carefully measuring and observing, we demonstrate that the total mass before and after the reaction stays the same, which confirms the law of conservation of masses. So remember, in any chemical change, the total mass remains constant. This is a fundamental concept that underpins all of chemistry. John Dalton was born in 1766 in England, into a poor weaver's family. Despite his humble beginnings, he started his career very early, becoming a teacher at just 12 years old. 7 years later, he advanced to become a school principal. In 1793, Dalton moved to Manchester to teach mathematics, physics, and chemistry at a college. He spent most of his life there dedicated to teaching and research. Then, in 1808, he introduced his atomic theory, which really changed the way scientists understood matter. Now, linking this to our broader theme, Dalton's work helped us understand that elements combine in specific fixed ratios. For example, Proust stated that in any chemical substance, elements are always present in definite proportions by mass. Take ammonia, NH4. No matter where it's from, nitrogen and hydrogen are always in a ratio of 14:3 by mass. Similarly, in water, H2O, hydrogen and oxygen are always in a mass ratio of 1:8. So if you decompose 9 grams of water, you'll always get 1 gram of hydrogen and 8 grams of oxygen. Lavoisier and other scientists observed that many compounds are made of 2 or more elements, and these compounds always contain the same elements in the same proportions, no matter where they come from. This idea is what we call the law of constant proportion. It's a fundamental concept that shows the consistency and predictability in chemical composition across different samples. Let's talk about how atoms come together to form compounds. They do so in ratios of small whole numbers, which helps explain the predictable proportions we see in chemistry. Now, an important point is that atoms of a given element are identical in both mass and chemical properties. This means every atom of, say, carbon behaves the same way. All matter around us is made up of these tiny particles called atoms, and these atoms participate in chemical reactions, whether they're breaking apart or combining to form new substances. When atoms form compounds, the number and types of atoms stay constant. That's what gives compounds their unique properties. Also, atoms of different elements have different masses and chemical behaviors, which is key to understanding chemical reactions and the diversity of matter. Another crucial idea is that atoms are indivisible particles. They can't be created or destroyed during chemical reactions, only rearranged. This concept was the cornerstone of Dalton's atomic theory, which states that all matter, whether it's an element, a compound, or a mixture, is made up of these small particles called atoms. Dalton's theory helps us understand the fundamental nature of matter and provides a foundation for much of modern chemistry. Let's take a closer look at the surface of silicon in this image. Now, to understand the scale we're dealing with, remember that 1 nanometer is equal to 1/1,000,000,000th of a meter, or 1109 meters. This helps us visualize just how small these structures are. Atomic radii, which tell us about the size of atoms, are measured in nanometers as well. For example, the size of an atom is approximately 10 to the minus 10 meters. To put that into perspective, if you lined up about 100 million atoms, they would stretch across just 1 centimeter, roughly the width of your fingernail. Now, considering the fundamental particles within an atom, the electron stands out because it's by far the least massive. It weighs only about 9.11 times 10 to the minus 31 kilograms, which is incredibly tiny. Plus, it carries a negative electrical charge. Its size is so small that current measurement techniques can't even determine its exact dimensions. So, in summary, atoms are extremely small, roughly 10 to the minus 10 meters in size, and understanding these scales helps us grasp the nanoscale world we're exploring, especially in materials like silicon. Now, let's take a closer look at Dalton's symbols of elements. On this slide, you'll see several symbols that represent different elements. These symbols are a key part of Dalton's atomic theory, as they provide a simple way to identify elements in chemical reactions and formulas. For example, we have oxygen, which is represented by the word oxygen in the slide, and hydrogen shown as hydrogen. These symbols are usually one or two letters with the first letter capitalized. Sometimes the second letter is lowercase, like in copper, which is represented as Cu, or lead, which is Pb. You'll notice various symbols here, such as C for carbon, Fe for iron, P for phosphorus, S for sulfur, Cu for copper, Pb for lead, Ag for silver, O for gold, Pt for platina, and Hg for mercury. These symbols make it easy for scientists to communicate precisely about elements without writing out the full name each time. Most importantly, Dalton's system was a big step forward because it standardized how we write chemical elements. This consistency helps us understand chemical equations, reactions, and compounds more clearly. It's a foundational concept that underpins much of modern chemistry. So, as we continue, keep in mind that these symbols are not just abbreviations. They're a universal language that connects scientists around the world. Let's talk about the modern symbols of elements. Many symbols are derived from the element's name in Latin, German, or Greek. For example, the symbol for iron is Fe, which comes from its Latin name, ferrum. Sodium's symbol Na is from its Latin name, natrium, and potassium's symbol, K, from kalium. Gold is O from aurum, and silver is Ag from argentum. Some symbols are simply the first one or two letters of the English name. For instance, hydrogen is H, aluminum is Al, but not Al, and cobalt is Co, not Co. Many symbols are formed by taking the first letter or two of the element's name in English. In the early days, element names often came from the place where they were first discovered. Take copper, for example. Its name was derived from Cyprus. Other names are based on colors, like gold, which got its name from the English word for yellow. Some symbols combine the first letter and a later letter in the name. For example, chlorine is Cl, zinc is Zn. It's important to note that the first letter of every symbol is always uppercase, and if there's a second letter, it's lowercase. Finally, IUPAC, the International Union of Pure and Applied Chemistry, is the organization responsible for officially approving the names, symbols, and units for elements. And historically, Ernst Jacob Berzelius was the scientist who suggested that element symbols should be made from one or two letters derived from their names, which is the system we still use today. Let's take a closer look at some common symbols of elements. As you can see, each element has a unique one or two-letter symbol that helps scientists communicate efficiently. For example, aluminum is represented by Al, which is derived from its name. Copper is Cu, from its Latin name cuprum. Nitrogen's symbol is simply N, and argon's is R. Notice that some symbols are just a letter, like nitrogen or oxygen, while others combine two letters, such as fluorine F or silicon C. These symbols are standardized and used globally, making it easier for us to understand chemical formulas and reactions across different languages and regions. Recognizing these symbols connects directly to the overall theme of understanding the building blocks of matter. Whether we're talking about elements in the environment, in industry, or in the human body, these symbols serve as a universal language. Some other interesting examples include gold, O, which comes from its Latin name aurum, and iron, Fe, from ferrum. Sodium is Na, from natrium, and potassium is K, from kalium. By familiarizing ourselves with these symbols, we gain a foundation for deeper studies in chemistry, helping us read and interpret scientific data more effectively. Atoms of most elements are not able to exist independently for very long. Instead, they tend to combine with other atoms to form molecules and ions. These molecules and ions are the building blocks of everything around us. When large numbers of these molecules or ions come together, they form the matter that we can see, feel, or touch every day. This is how atoms, which are tiny and individual, ultimately contribute to the tangible world we experience. It's a fundamental process that connects the tiny world of atoms to the larger world of matter, helping us understand how everything is built from the smallest particles. Now let's talk about how we determine the relative atomic masses of atoms. All these masses have been measured with respect to a specific standard, which is an atom of carbon-12. Since 1961, the universally accepted atomic mass unit, or AMU, has been based on this carbon-12 isotope. In fact, the latest IUPAC recommendations now write this unit as U, which stands for unified mass, or sometimes as Dalton, abbreviated as DA. The key point here is that one atomic mass unit is exactly 1/12 of the mass of a carbon-12 atom. Because atoms are incredibly tiny, directly measuring their mass is quite challenging. So, scientists compare an atom's mass to that of a standard atom, usually the one with the nearest whole number mass, to make the measurement more manageable. This approach helps us understand atomic mass in a consistent way, and connects back to the overall theme of how we measure and understand the fundamental building blocks of matter. Let's take a closer look at the first 20 elements of the periodic table. As we go through, I'll highlight some key points to help deepen your understanding. Starting with hydrogen, which has the symbol H, it's the simplest element with an atomic number of 1, meaning it has just 1 proton and 1 electron. Moving to helium, with the symbol He and atomic number 2, it has 2 electrons and protons and an atomic mass of 4. Helium is a noble gas, so it has a full outer shell and no valency. Next, lithium, symbol Li with atomic number 3, has 3 electrons and protons, and it's in group 1, which means it has a valency of +1. Beryllium, with symbol B and atomic number 4, has 4 electrons, and its valency is +2. Boron, symbol B with atomic number 5, has 5 electrons and a valency of +3. Carbon, C, atomic number 6, has 6 electrons and a neutral valency, which makes it incredibly versatile in forming bonds. Nitrogen, N with atomic number 7, has 7 electrons and a valency of -3, while oxygen, O with atomic number 8, has 8 electrons and a valency of -2. Fluorine, F, atomic number 9, is highly reactive with 7 electrons in its outer shell, giving it a valency of -1. Neon, Ni, with atomic number 10, is a noble gas with a full outer shell, so it has no valency. Moving to the alkali metals, sodium, Na, with atomic number 11, has 11 electrons and a valency of +1, and magnesium, Mg, with atomic number 12, has a valency of +2. Aluminum, Al, with atomic number 13, has a valency of +3. Then we have silicon, C, with atomic number 14, which has 4 valence electrons, making it a tetravalent element. Phosphorus, P, with atomic number 15, has 5 valence electrons and a valency of -3. Sulfur, S, atomic number 16, has 6 valence electrons and a valency of -2. Chlorine, Cl, with atomic number 17, has 7 valence electrons, giving it a valency of -1. Argon, R, atomic number 18, is another noble gas with a full outer shell, so it has no valency. Moving on, potassium, K, with atomic number 19, has a valency of +1, and calcium, Ka, with atomic number 20, has a valency of +2. These first 20 elements lay the foundation for understanding how elements combine and interact based on their electron configurations and valencies. Recognizing these patterns helps us understand the chemical behavior of each element and their role in various compounds. Now let's take a closer look at the caffeine molecule, which has the chemical formula C8H10N4O2, and is also known as 1,3,7-trimethylxanthine. This is its official chemical name. What's really interesting about molecules like this is that they are made up of atoms of the same element or different elements, that come together to form a single, stable unit. A molecule can be thought of as the smallest particle of an element or a compound that can still exist on its own and display all the properties we associate with that substance. In general, a molecule is usually a group of two or more atoms that are chemically bonded, meaning they are held together by attractive forces, which are quite strong. This bonding is what gives molecules their distinct characteristics and allows them to participate in chemical reactions. So, in the case of caffeine, its atoms are arranged in a specific structure that defines its properties, making it a fascinating example of how tiny particles combine to create something with a particular effect. Understanding molecules like caffeine helps us see how the smallest building blocks of matter influence the larger biological and chemical processes around us. Let's take a closer look at the concept of atomicity. This term refers to the number of atoms that make up a single molecule. It's a fundamental idea because it helps us understand the composition of different molecules. For example, some elements like argon and helium have molecules that are just a single atom. These are called monatomic molecules. You see, in these cases, the molecules consist of only one atom, so their atomicity is 1. However, in most nonmetals, molecules are made up of more than one atom. Take oxygen, for instance. A molecule of oxygen, O2, is made of two oxygen atoms bonded together. When a molecule has two atoms, we call it diatomic. But if three oxygen atoms join together, forming O3, that's ozone, a triatomic molecule. Another key point is that molecules of an element are always made up of the same kind of atoms. So, oxygen molecules are always just oxygen atoms, and nitrogen molecules are just nitrogen atoms. This uniformity is what defines an element's molecular structure. Understanding these concepts about atomicity and molecular composition helps us see how elements combine and form different molecules, which is essential in grasping the nature of matter itself. Let's take a closer look at the atomicity of some common elements. Atomicity refers to the number of atoms that are grouped together and behave as a single unit in their natural form. For example, many elements exist as monatomic, meaning they consist of single atoms. Argon and helium are perfect examples of this, both being monatomic gases. On the other hand, some elements are diatomic, which means they naturally occur as molecules made up of two atoms bonded together. Oxygen, hydrogen, nitrogen, and chlorine all fall into this category. Recognizing these diatomic molecules is important because their behavior in chemical reactions depends on the fact that they're paired up. We also see elements that are polyatomic, like phosphorus and sulfur. Phosphorus typically exists as P4 and sulfur as S8, which means they form molecules made of 4 or 8 atoms, respectively. These polyatomic molecules tend to have different properties compared to monatomic or diatomic forms. Now, when we look at metals, most of them, such as sodium, iron, aluminum, and copper, are found naturally as monatomic atoms, although they often form metallic bonds in their solid state. This means, in their pure elemental form, they typically exist as single atoms, which is crucial for understanding their reactivity and bonding behavior. Understanding the atomicity of elements helps us grasp how they behave chemically and physically. It's a key concept that ties into the overall theme of how elements interact and combine to form compounds. According to Dalton's atomic theory, atoms combine in the ratio of small whole numbers to form molecules of compounds. This means that when elements come together to create a compound, they do so in simple, whole number ratios, which is a fundamental idea in understanding how chemical compounds are formed. The ratio of elements in a molecule of a given compound will always remain the same, regardless of the method or source from which it is obtained. So, whether you find that compound in a lab, in nature, or synthesize it yourself, the proportions of the elements involved will stay consistent. This consistency is key to identifying and classifying compounds. Finally, atoms of different elements join together in definite proportions to form molecules of compounds. This highlights that these combinations are not random, but follow specific, fixed ratios, which helps us predict and understand the composition of different substances. All of these points reinforce the idea that molecules of a compound have a specific, predictable structure, which is essential for understanding chemical behavior and reactions. Let's take a closer look at some common compounds and their molecules. As you can see in the table, each compound is made up of specific elements combined in certain ratios by mass. For example, water, which we all know well, consists of hydrogen and oxygen. The ratio by mass is about 1 to 8, meaning for every part of hydrogen, there are 8 parts of oxygen. Moving to ammonia, which is used in cleaning products, it's made of nitrogen and hydrogen. Here, the ratio is roughly 14 to 3, indicating a heavier proportion of nitrogen compared to hydrogen. Then we have carbon dioxide, a gas we encounter daily, especially in respiration and combustion. It's composed of carbon and oxygen with a ratio of 3 to 8 by mass. Magnesium sulfide, an interesting compound used in various industrial applications, combines magnesium and sulfur in a 3 to 4 ratio. Finally, sodium chloride, or common table salt, is made up of sodium and chlorine. Its ratio is approximately 23 to 35.5 by mass, reflecting the typical proportions found in salt crystals. Overall, understanding these ratios helps us grasp how elements combine to form different compounds, which is fundamental in chemistry. It shows that the properties of a compound depend heavily on the specific elements involved and their ratios. Now, let's look at how ions can be separated using a process called electrolysis. This technique is quite useful in various applications, including purifying metals and producing chemicals. Next, it's important to understand what a polyatomic ion is. Essentially, it's a group of atoms that carry an overall electric charge. For example, when we look at sodium chloride, or NaCl, it's made up of sodium ions, which are positively charged, and chloride ions, which are negatively charged. Speaking of charges, a negatively charged ion is known as an anion. Conversely, a positively charged ion is called a cation. These charges are crucial because they determine how ions interact and move in different chemical processes. Ions can be quite diverse. They might consist of just a single atom or a group of atoms that together have a net charge. This variability allows for a wide range of compounds and reactions in chemistry. Also, remember that ions can be either negatively or positively charged. This duality is fundamental to understanding how compounds form and how they behave in solutions. Now, in many compounds, especially those made of metals and nonmetals, you'll find these charged species, the ions, that are essential for conducting electricity and forming various chemical bonds. Finally, to help us identify these ions, there's a table of names and symbols for some common ions, along with their valencies, which tell us how many charges they carry. Understanding these key points helps us grasp the broader picture of chemical behavior and reactions involving ions. Valency is the combining power of an element. When we talk about valency, we're referring to how many electrons an element can share, gain, or lose to form chemical bonds. Think of it as the element's ability to connect with other atoms. This concept is really important because it helps us understand how elements interact and form compounds. For example, if an element has a valency of 1, it can form 1 bond, while an element with a valency of 4 can form 4 bonds. Recognizing valency helps us predict the formulas of compounds and understand their properties. So, in essence, valency is a key idea that ties together how elements combine to create the vast array of substances around us. When a compound is made up of a metal and a nonmetal, the convention is to write the name or symbol of the metal first. For example, you might see calcium chloride, which has the chemical formula CaCl2, or sodium chloride, NaCl. Other examples include iron sulfide, Fe(S), and copper oxide, CuO. Now, when it comes to writing the actual chemical formulas, there are some important rules to keep in mind. One key point is that in compounds formed with polyatomic ions, we use brackets to show the number of ions present. For instance, magnesium hydroxide, MgO2, indicates that there are 2 hydroxide ions for each magnesium ion. If only one polyatomic ion is involved, like in sodium hydroxide, NaOH, then we don't need brackets. Another critical concept is that the valencies and charges on the ions must always balance out. This means the total positive charge should equal the total negative charge, ensuring the compound is electrically neutral. Before we can write these formulas properly, we need to know the symbols and valencies of the elements involved. Getting comfortable with these basics helps us accurately construct chemical formulas and understand how different elements combine chemically. When writing chemical formulas, we use brackets whenever there are 2 or more of the same ions in the formula. This helps us keep everything clear and organized. The valency, which is the combining power of an element, typically ranges from 1 to 2 for many elements we encounter. For example, consider hydrogen sulfide, which has the formula H2S here. The 2 hydrogen atoms are written before the sulfur atom, and the subscript 2 indicates there are 2 hydrogens. Let's look at another example, hydrogen chloride with the formula HCl. In this case, hydrogen has a valency of 1, and chlorine also has a valency of 1. When we write these formulas, we start by writing the symbols of the elements and their valencies below them. The key step is crossing over those valencies, meaning we transfer the valency numbers to the opposite elements to balance the formula correctly. So, in summary, understanding how to write these formulas involves knotting the valencies and crossing them over to ensure the compound is chemically balanced. This process is fundamental for correctly representing simple compounds in chemistry. Let's look at how we determine the molecular mass of different substances. First, remember that the atomic mass of oxygen is 16 atomic mass units, or 16U. The molecular mass of a substance is simply the sum of the atomic masses of all the atoms that make up a molecule of that substance. For example, in HNO3, the molecular mass is calculated by adding the atomic mass of hydrogen, nitrogen, and oxygen. That is, 1 hydrogen atom with a mass of 1U, 1 nitrogen atom with a mass of 14U, and 3 oxygen atoms, each with a mass of 16U. So 1 plus 14 plus 3 times 16 gives us the total molecular mass of 63U. Now let's look at water. H2O water contains 2 hydrogen atoms and 1 oxygen atom. The atomic mass of hydrogen is 1U, and oxygen is 16U. So the molecular mass is calculated as 2 times 1 plus 16, which totals 18U. This example illustrates how we extend the concept of atomic mass to find the molecular mass of compounds. It's a fundamental step in understanding chemical quantities and reactions. Let's look at an example with NaCl. Its formula unit consists of 1 sodium atom and 1 chloride atom. To find its formula unit mass, we multiply the atomic mass of sodium, which is 23, by 1, and the atomic mass of chlorine, which is 35.5 by 1. Then, we add those together, giving us a total of 58.5 atomic mass units. This process is very similar to how we calculate molecular mass, but the key difference is that we use the term formula unit when we're talking about compounds whose particles are ions. The formula unit mass of a substance is essentially the sum of the atomic masses of all the atoms in one formula unit of that compound. Understanding this helps us connect the mass of the particles we're dealing with to the overall structure and composition of ionic compounds, which is a core part of mastering chemical calculations. So, to sum up, we can say that 1 mole of any element is equal to 6.022 times 10 to the power of 23 particles of that element. This could be atoms, molecules, ions, or other discrete entities. And importantly, the mole also corresponds to the relative mass in grams of that element. For example, 1 mole of oxygen is 16 grams, which contains 6.022 times 10 to the 23rd particles. This fixed number of particles, 6.022 times 10 to the 23rd, is known as Avogadro's number, or N0. It's a fundamental constant in chemistry. The concept of the mole was introduced by Wilhelm Ostwald back in 1896, and it's really a way to bridge the microscopic world of atoms and molecules with the macroscopic world we can measure. Think of the mole as similar to other counting units like a pair, a dozen, or a gross. It provides a clear, consistent way to measure the amount of substance, especially when dealing with large numbers of tiny particles. And that's why the mole is so central to understanding how matter behaves and interacts at the atomic and molecular levels. Now, for easy access to more practice and solutions, you can simply click on the link that says Atom and Molecule NCERT Solution. Alternatively, you can go directly to the NCERT exercise section for detailed exercises and their solutions. This way, you can reinforce your understanding of atoms and molecules, which are fundamental concepts in chemistry. Remember, practicing these problems helps solidify your knowledge and prepares you better for exams. So, don't forget to explore the NCERT exercises for a comprehensive grasp of the topic.